Let's now try to think of a mechanism for the Grignard nucleophilic addition on aldehydes and ketones. Let's draw the structure of the general aldehyde like that again. So one way to do this is to write the Grignard like that. So what happens is that oxygen being Lewis basic, magnesium being Lewis acidic, can actually interact like that in a Lewis base, Lewis acid reaction, if you like, coordination. Now this coordination, or this Lewis acid Lewis base reaction, if you recall, actually enhances the electrophilicity of that carbon. This reaction between the Lewis base and the Lewis acid makes that carbon more electrophilic, in other words, more susceptible to nucleophilic attack. So now we take electrons from this Mg carbon bond, if you like, a carbanion in a way. It can be viewed as a carbanion. Remember that carbon that's bonded to magnesium, not only it's nucleophilic, it is also basic. So the carbanion, therefore, can attack the aldehyde like that in nucleophilic addition reaction. So what we get is this intermediate now. And now we have OMG X. You can write it like that. After the coordination, or even after the nucleophilic addition, we get an alkoxide which would react with Mg being a Lewis acid. We get that intermediate. Now this is not different really from this form where that OMG is viewed as an ionic bond. That's not really different. Okay, these two are basically the same. If you react this alkoxide intermediate with H3O plus, it gets actually protonated to give the final alcohol product. If you react it with H3O plus, and this mechanistically should be straightforward. We can show this with movement or with indication of electron movement, something like that. So the alkoxide picks up a proton from the hydronium ion to give finally the final alcohol product, and of course water. So this is a Grignard, a mechanism for the Grignard addition reaction on aldehydes in general to give the corresponding secondary alcohols.